In the section on related rates in calculus, one of the first problems that usually is presented involves a circular wave. So in this question we got a pebble dropped into a pool of water produces a circular wave which travels outward at a constant speed. Now, when you're setting up your variables, remember this is a rate, and we're looking for a rate of change of area under two conditions here. One when the area is 400 pi square centimeters, and one 4 seconds after the pebble was dropped into the pool. Now, we're given the rate of change of radius, so that's a dr dt. You can tell right from the units involved here that that's a rate. It's centimeters per second dr dt. And we have to find the rate of change of area with respect to t. So the link up here is the area formula for a circle, a equals pi r squared. And remember, we're taking the derivative with respect to time. This is actually what we call implicit differentiation. dA dt equals 2 pi r dr dt. And usually I just write an a prime and an r prime, but you have to keep in mind that these are derivatives with respect to time, even though the t is not present in the equation. Now, the first condition was that the area was 400 pi square units. So we take the area formula, pi r squared. When they give you a number involving a pi, it actually makes it simpler for you because you can just divide both sides by pi. R squared is 400, which gives us a radius of 20. So all we have to do is go to this formula right here. The rate of change of area is 2 pi times the radius, which we just found to be 20, times the rate of change of radius, which was given 15 centimeters per second, and we can work that out, and that'll be so many square centimeters per second for the change of area. Part B of the question was to figure out what happened after 4 seconds. Well, you see, since the rate of change of radius is 15 centimeters per second, that means that after 4 seconds the radius has moved out 4 times 15, or 60 centimeters. And again, all we have to do is put that radius into our derivative formula here. 60 for the radius, again 15 for the rate of change of radius, and that gives us our rate of change of area with respect to time. Now the second problem I'm going to look at here involves a sphere. The spherical balloon is being inflated at this rate, cubic centimeters per second, so that's a dA dt, I'm sorry, dV dt, because that's a volume, rate of change of volume with respect to time. And we have to find the rate at which the radius is increasing, again, under two conditions, a given volume and a given surface area. As I mentioned when we read the question, the rate of change of volume with respect to time is 8 cubic centimeters per second, and we have to find the rate of change of radius. Now, this is the volume formula for a sphere, linking the given and what we want to find, the V and the R. Again, we're taking the derivative with respect to time, so that's why on the end of this you see the 3 comes down when you're taking the derivative. 3 times 4/3 is just 4 pi r squared dr dt. So again, it's implicit differentiation. And once again, I prefer to just write V prime and R prime for the rate of change of volume and radius in terms of time. I rearranged the formula here. I divided both sides by 4 pi r squared because I'm looking for r prime, the rate of change of radius at particular times. Now the first given gave us a volume of 500 cubic units. So again, I go back to the volume formula. I cross multiply 3 times the 500 is 1500, and then divide by the 4 pi. Worked that out on my calculator, took the cube root, and then just plug these numbers into the R prime formula right here. R prime equals V prime, which was given to be 8 over 4 pi times the radius squared, and we just figured out the radius right there. And that gives us our rate of change of radius in terms of centimeters per second. Part B gave us a particular surface area. So we use a surface area formula for a sphere, which is 4 pi r squared. The surface area was given to be 80. So once again we divide by 4 pi to get the r squared alone and work this out and take the square root to get the r value. And once again go back to this formula, r prime equals, and again put in the v prime and the radius that we worked out there. One last thing, you notice when we wrote this formula that was actually the surface area formula on the bottom. So we could have gone about it this way. Instead of going to all the trouble of working out the r value, we could just say the 4 pi r squared is the surface area, put in the given surface area, which was 80, and as you can see here you get the same answer, 0.1 centimeters per second. So it's just a little faster way of doing it without actually finding the radius of the sphere.